Because continuous functions and limits of functions are so intimately tied together, and functional limits are so intimately tied together with limits of sequences, the following theorem doesn't even deserve a proof. Theorem: let f comma g from a to r be functions that are continuous at x in a. Then number 1, f plus g is continuous at x. Number 2, I will write f plus or minus. Then fg is continuous at x. Number 3, cf is continuous at x, where c is a real number. Then number 4, f by g is continuous at x provided g is not equal to 0 on a. Of course, the last thing can be finessed and a better version be made, but I am not going to bother doing it. So this theorem just follows immediately from all the theory that we have so far developed. Okay, now suppose I were to ask you, look at the function square root of 3x squared plus 5. Is this function continuous? First of all, what is the domain of the function? The domain of the function is the whole of the real numbers. It's the whole of the real numbers, because there's an x squared that in term inside the square root will never be 0. It will be well defined. We already know that because of this previous algebraic theorem where sums, products, etc. of continuous functions is continuous, 3x squared plus 5 will be continuous. And we also know that square root will be continuous because that's what we proved in an earlier module. But we cannot combine these two in any simple way to show that root of 3x squared plus 5 is continuous just by using this algebraic theorem. Well, no problem. I will just prove what is needed. Let f from a to r and g from b to r be functions with f of a subset of b. Okay, if f is continuous at x in a and g is continuous at f of x, which is an element of b, then g composed with f, which is a function from a to r, is continuous at the point x. Okay, proof. This proof is best done using open balls around the point that we are interested in. Let epsilon greater than 0 and consider the open ball be g composed with f of x epsilon. Okay. Now, by the various characterizations of continuity that we have seen along with properties of limits, it is sufficient to show that we can find delta greater than 0 satisfying f of b x delta is fully contained in, not f of, sorry about that, g composed with f is fully contained in b g of x epsilon. If we can do this, then we are done. Okay. How does one do this? Well, we can find delta 1 such that g of b f of x delta is a subset of b g of f x epsilon. Why can we do this? Because g is continuous at f of x. Right? Now we can find delta 2. I'll just call it delta. We can find delta greater than 0 such that f of b x delta is fully contained in b of f of x delta, because f is continuous, at x. Putting 2 and 2 together, we get 4, which is what we want. G of f of b x delta is contained in g of b f of x delta, which is contained in b of g circle f x epsilon. This is just one moment. This is delta 1. These are all delta 1. Okay. So this completes the proof. So this was fairly easy when we used open balls. So the moral of the story is, we always try to characterize a definition in as many different forms as possible. This is because given any situation, you need to use the right tool for the job. When all you have in your hand is a hammer, everything starts to look like a nail. But you would wish to have a saw, a screwdriver, a spanner, and so on. So we have characterized continuity in several different ways. Use the characterizations wisely. This is a course on real analysis, and you have just watched a module on operations on continuous functions.